Hey everyone, welcome to my channel. I come from China, and the content developed in this video is mainly in Chinese. First off, I want to share my thoughts. Most of the programming knowledge I've gained while working on this robotic arm comes from various creators and experts online. I've learned a lot from the community, and I hope to give back in some way. I'm still learning myself, so please bear with me if the video production isn't perfect. Now, let me introduce this video. The structure of this robotic arm was actually completed a while ago, but I put it on hold to focus on writing a paper. I got inspired to create this robotic arm after watching videos from Jihui Jun. Amazing stuff. Since I have a background in mechanical engineering and previously worked at a robotics company, designing this mechanical structure wasn't too challenging for me. However, I hadn't really delved into embedded systems or hardware programming, so I always thought it was impressive to design something and make it move. After starting my master's program, I decided it was time to seriously improve my skills in this area. I didn't make the most of my undergrad years, so I can't afford to waste any more time. Initially, I created a robotic arm and managed to assemble all the 3D printed parts, but I was still a beginner in embedded systems at that point. Since then, I've experimented with various projects and continuously learned. I feel I'm finally getting the hang of it. The arm structure is designed, and for the circuit part, I just need a main control board. The motors for each joint are off-the-shelf products, so writing the control logic shouldn't be too difficult. I decided to continue improving this robotic arm. Let's start with an overview of the robotic arm structure. The joint arrangement of this arm is actually modeled after the UR robotic arm, though I haven't taken apart a UR arm to see what motor modules it uses. As a student, my budget constraints limit me to using stepper motors with closed-loop drives. Initially, I wanted to replicate the drive system used by Jihui Jun, but after assembling the board, I realized that my soldering skills were lacking. I don't even own a soldering station. After wasting 3 boards, I decided to give up on that approach. I then considered using drivers from 3D printer setups, like the A4988, TMC series, or the DRV series. However, after some hands-on experience, I found that if a stepper motor loses steps, there's really not much you can do about it. While I didn't expect the robotic arm to be perfect, I needed it to operate stably. Eventually, I stumbled upon a creator who used a Zhongde 2 driver, so I searched for it and bought a couple to test. To my surprise, they worked well. Similar functionality, featuring a Hall encoder combined with a 4-channel half-bridge driving FOC algorithm. This is what I'm using now, with a driver for a 57 stepper motor, and they have options for 42, 35, and 28 stepper motors as well. With the drive issue sorted, the next challenge was torque. Since I'm using quite a few stepper motors, I knew that given the length and load of this robotic arm, a direct drive from the motor wouldn't be practical. Even with a synchronous belt, I could only manage a maximum reduction ratio of 10, and I also considered using a planetary gearbox, but the gearboxes with low back clearance are typically over 300 renminbi. That's when I discovered the Puying gearbox I'm currently using. While it might not be suitable for commercial products, it's perfectly adequate for my experiments. One motor module, the simple version, is just about right. One downside, though, is that the gearbox output doesn't have an encoder. Why an output encoder is necessary? To put it simply, the output encoder is crucial because after the motor passes through the gearbox, the speed is reduced while torque is increased. The shaft behind the motor has a permanent magnet with a Hall encoder for positioning, which only helps determine the position of the motor rotor. However, if the motor rotates more than one full turn, the Hall encoder won't know where the motor is positioned. While it's possible to keep track of the count through software, if power is lost and the robotic arm is moved, the control program's zero position can become inaccurate. This is why industrial and collaborative robotic arms are designed with both input and output closed-loop systems, whereas low-cost servos typically only have an output closed-loop. In my robotic arm, there isn't an output closed-loop. I considered using a hollow encoder, but the cost was too high, so I opted out. Initially, I thought about using a current loop to record the zero position when the joints hit their limits. This approach is feasible but would require a lot of time, so I abandoned it. As a result, I have to manually set the zero position each time, which is more of a subjective feeling than an exact measure. Now, let's discuss the structure of the robotic arm. It is divided into 6 parts, as shown in the diagram. The first 5 axes each have a motor paired with a harmonic gearbox, and the output of the gearbox connects to the flange plate of the preceding component. The overall design is structured like a nesting doll, primarily to facilitate 3D printing. If I had access to CNC machined aluminum, this would be less difficulty. Considering that the Z-axis strength is relatively weak when 3D printed, I purchased ready-made aluminum tubes for the 2 long connecting rods. They are inexpensive and effective. The definition of the 6 axes in the robotic arm is as follows. The first axis uses a longer 48mm 42 motor, the second axis has a standard length, 37.5mm, the third axis is short, 23mm, using a 42 stepper motor, while the fourth and fifth axes use 35 stepper motors, and the sixth axis uses a 28 stepper motor. Now, let's talk about the hardware section, though there's not much to say. The PCB I designed follows the principle of just use that what you can buy. I'm using the ESP32 as the main microcontroller. The Zhongde2 driver I'm utilizing is a bus driver that also supports the pulse control method commonly used in standard 3D printers. To briefly explain bus driving, as shown in the diagram, it involves connecting multiple terminals with 2 or more bus lines, with other peripheral modules wired in parallel. Somewhat like how the neutral and live wires connect in a home. Common bus communication protocols include I2C, SPI, Serial, CAN, and EtherCAT, but each has its own communication logic. I'm not an expert, so if you're interested, feel free to look them up. For my project, I'm using serial communication. Although the driver supports CAN bus, the ESP32 requires an additional module for that, and since I don't need high communication speeds, simple serial works fine. On the PCB, the 2.54mm 4-pin connectors are for the motors, and they are all identical, so it doesn't matter which one you use. The DC power input is directly connected to these motor ports. There are also 2 voltage regulators on the board, stepping down to 9V and 5V, with ports for connecting to these voltages located on the side of the board. These serial ports use different pins. My ESP32 supports 3 hardware serial ports, and to avoid resource conflicts, I used other serial ports to connect peripherals. On the right side of the board, there are 2 I2C ports connected to the 5V supply, and below that, I've set up 2 PWM input and output pins. The PWM inputs are primarily for potentiometers or other sensors, while the PWM outputs are intended for controlling servos. Since I'm using bus servos at the end of the robotic arm, which also connect via serial, those specific PWM ports are not utilized. Next, let's dive into the software section. I based my software on the Arduino platform because I wanted to quickly develop some functionalities. Learning STM32 would have taken too long, and time was limited. I initially got inspiration from a project by Xiaoji, who shared the complete source code for his robotic arm competition. After studying it extensively, I started writing my own code, which is mainly divided into 2 main parts: single-axis control and inverse kinematics control for 3 axes. Additionally, I've included libraries for the Zhongde2 stepper motors, a servo library, Bluetooth integration, serial reception, and a custom data conversion library for convenience. I won't go into all the internal logic, but I have some simple comments in the code. If anyone is interested, feel free to check it out. Now, let's look at some functional demonstrations. When you open the app and click on Search, you can find the device by name, leading you to the device selection interface. After selecting UR5, you enter the UR Robot Control page, which features single-axis motion control with position and speed modes. I implemented kinematic control for just the first 3 axes. The 6-axis arm presents multiple solutions, which require additional control logic, so I haven't tackled it yet, though I plan to enhance it in the future. The 3-axis kinematics focuses on movements in the X, Y, and Z directions, with selectable motion amplitudes of 1mm, 10mm, or 50mm. While I haven't developed the kinematics for the latter 3 axes, I did implement a simple angle overlay to keep the pitch of the 4th axis and the roll of the 5th axis constant. The app interface also allows for separate control of the 5th axis's roll angle. To simplify claw position control, I added features for upper, middle, and lower claw placements, while the angles for the 4th and 5th axes adjust accordingly for the other 2 positions. Finally, at the end of the video, I'd like to share my thoughts. The internet today is incredibly advanced, making it easy to access any knowledge you want to learn. With my prior work experience, I've had few issues with structural design. However, I've often struggled with having bold ideas but only being able to create something that looks good but doesn't function well. A year ago, I started from scratch in embedded systems, and the more I learn, the more I realize how much there is still to understand. There are many experts online, and as an ordinary person, I can really feel the gap. It's important to take it slow and learn step by step. The learning process is all about making steady progress.